go ahead and get started. So first of all, welcome back. Hope y'all had a nice spring break. And we are now in the home stretch of things. So we have, it's hard to believe, but 3 weeks left, and that is it. So for better or for worse, right? The first thing I wanted to remind you about is don't forget that your third midterm exam is coming up on Wednesday, so our next meeting. And that will cover the, depending on how you count, 3 or 4 chapters since the previous exam, specifically C13, the chemistry of amines, the carboxylic acids, and the acid derivatives, which we will wrap up today. So we have largely finished with the derivatives. We had to get through a little bit of amide chemistry and then nitrile chemistry, but we will certainly finish that today. And then I thought, in addition to that, once we finish, I would give you just kind of a random mechanism problem to work on. You could spend, 10, 15 minutes working on that by yourself or with someone else. And then we could go over it together. Mechanism problems seem to be one of the harder classes of problems on these exams. And so, the more practice you get with them, I think the better off you'll be. So I think it's time well spent. So we may end up jumping into a little bit of the Unit 4 material, just introducing that at the end of today, but we'll just see how that goes. Before we jump back into things, does anybody have questions for me on anything? Yeah.
3 more weeks and we're gonna have another midterm?
Yeah.
Is that like in 2 weeks?
No, it'll be the 4th midterm will be the final day of the semester.
Oh. So that means we don't have time to study for finals, right?
Well, you'll be studying for the final because the uniform material is on the final.
So when is the final?
The ACS is going to be your normal scheduled final exam time. So, which is
like a week later.
Yeah, about a week later.
So we have a study in no school, right?
Right.
Correct.
Yeah, we don't.
Yeah, just.
Oh, okay.
You'll finish up. I think the semester ends on a Wednesday this semester, so that will be where you have your exam for, and then the following week, and that's when classes end, and finals begin that Thursday, and just depending on what classes you have and when those finals are scheduled.
So I guess the final is Monday. We take the midterm Wednesday and the final will be Monday.
Yeah.
Oh, so that's not a
Well, I was hoping
Oh, I
for
need
next
to
week.
take off.
No, that's graduation day on
Oh.
Wednesday.
So, but yeah, that's how things are laid out.
That is such a tight.
So, any other questions on what's coming up or anything else?
When do we start the project?
You'll start that. This week is experiment 11. You'll start that in 2 weeks.
Okay.
Yeah.
So only experiment 11 left and then we're gonna.
Well, experiment 13 as well.
Oh.
Yeah.
So when is that?
You
It's gonna be
thought,
hard.
you thought we have to study for the exam and then do the research and then also study for finals.
Yeah. The project is not going to be anything really
Oh.
stressful or out of the ordinary. It's just basically doing 2 reactions. The reason I call it a project is because everybody's getting their own reagents, and as a result, because everybody's going to get their own reagents and create their own product, everybody ends up kind of dealing with their own specific issues. So the issues that you're going to run into on your synthesis are not going to be the same as the issues that Ethan runs into on his synthesis, because you're starting with different reactants and forming different products. So the reaction is going to be the same. You're just, because you're dealing with different reagents, you might have different issues of solubility, which is going to lead to different methods of purification, so that's really the only, I mean, in terms of the chemistry, it's not anything different than any other lab you've done. Okay? So I wouldn't stress too much about that. And I'll give you a little insight into the future. So you do have to write a formal report for that. However, what I've started doing in recent past is if you look at the way the points are laid out in the syllabus, that project is worth, I think it's
40 points.
okay, thank you, 40 points. So double what a normal formal report is, right? But if you would prefer not to spend time doing that and focus your efforts on getting ready for the exams, I make that optional. So it's not going to harm you. If you decide, no, I don't want to do it, then your overall grade at the end is going to be worth 40 points, or the total points that you can collect at the end is going to be 40 less than what's in the syllabus. So it's not going to hurt you at all if you decide not to do it. But the reason I have it in there as an option is because if you're like right on the cusp of a grade, doing that project and doing well on it might push you up into the higher grade. But if you're like sitting kind of in the middle of a grade, I'm probably not going to really do anything for you or against you, and so you may as well just not write the report. So that could allow you some extra time and take a little bit off of your plate if you decide to take that option in that last week of classes.
I wish you could make it extra credit.
Do what?
Make it an extra credit, so.
Technically, it is extra.
Yeah, it kind of is extra credit though.
Not really, I mean,
Not
if you do bad on it, doesn't that drop your
Right.
grade?
Well, yeah, but
That's not extra credit, you're saying.
If you don't do it, it doesn't impact you.
I'm usually pretty lenient, and as long as you don't turn in a heap of garbage, you're going to do pretty well on it. So that's kind of another option to think about. Usually I kind of wait until we get into that, but since the conversation worked its way in that direction, but again, something to think about. You don't have to make the decision now, obviously, but it is an option for you. All right. Any other questions?
For the ACS, right, do we have to pass it, or do we just have to take it?
No, it's going to count just like another exam.
Okay.
So you don't have to necessarily get a specific grade in order to pass the class. It's just going to get factored into your grade just like any other exam would.
Well,
Oh, and that reminds me, since we're on the topic, I do have ACS study guides available to check out. So if you are interested in checking one of those out, just let me know, remind me. They are in the lab, and so just tell me at some point while we're in lab if you would like to check one out, and I can let you have one of those to borrow. Okay.
That's Chem 1 and 2.
Correct.
Ooh.
Yeah. All right. Okay, so let's go ahead and get back into it. So where we stopped last time, actually, let me start recording this. Okay, so at our last meeting where we ended, we were just introducing the chemistry of the amides. And what we finished talking about last time was we were saying how, in a relative sense, how non-reactive the amide was towards nucleophilic substitution for a whole variety of reasons. So none of these reactions are going to be terrible, are going to be very easy to do. Okay, they're going to require very harsh conditions for the most part. Reaction times will be quite long. They are just not terribly reactive towards nucleophilic substitution. I think we talked about the synthesis. There are two main ways of synthesizing the amides. Number one was one way that you've known about for a while, which is taking an amine and adding it to an acid halide, so you can make amides that way. The second way was a rather new way, something we haven't talked about before, and that was those coupling agents. And that's the way amides are most commonly made these days, using these coupling agents. I gave you a couple examples of that, something like DCC, dicyclohexylcarbodiamide, DIC, diisopropyl carbodiamide. And those of you that have the method 3 for experiment 11, or method C, I can't remember if it's a letter or a number, you guys too will be using a specific coupling agent today, one that's called Hatsu. But in any case, that is the most common way these amide bonds are made today, is using the coupling agents, because they do so under rather mild conditions. So as we get into the reactions of the amides, the first one we'll look at is reduction. So you already know this one as well. But before we jump into what the reduction of an amide looks like, maybe we can just kind of quickly review, just to get us thinking about these derivatives again. If you were to take an acid chloride, and remember with these reductions we're typically using LAH, what functional group resulted from the reduction of an acid halide? Anybody remember? What did you say?
Is it an alcohol?
It was an alcohol. You got the primary alcohol. All right. With the acid anhydrides, if we reduced those with LAH, anybody remember the functional group we got here?
Should be alcohol.
Yep, exactly the same. Primary alcohol. If you had the ester and treated it with LAH, what functional group did we get here?
Same thing.
Yep.
Alcohol.
Notice the trend. Now, if we start with an amide, we've talked about the reduction of amides before. We talked about this when we were doing the amine chemistry. What functional group do we get from the reduction of an amide?
I mean,
Yeah, not the primary alcohol. All right, so we kind of buck the trend here, and you make the amine. So I think that's worthwhile getting into a bit. So why is it that all of the other derivatives that we talked about so far reduce to give primary alcohols, yet the amides reduce to give amines? So we'll just go through the mechanism quickly. So we can oftentimes think of LAH as just a source of H-, and if you do that, the hydride will attack, just as we've seen many times before. And you get something like this. Now, what might be tempting to think is, normally what we've seen is that in these substitution mechanisms, the carbonyl reforms and you kick out a leaving group. Well, imagine what that would require. Carbonyl reforms and you kick out NH2. That's an NH2 minus leaving group. NH2 minus is an exceptionally strong base and thus is an exceptionally bad leaving group. So I want to, again, I'm not going to be that concerned that you know this mechanism because it's more of an organometallic mechanism, but I do want to show it to you just to illustrate a better mechanism and to hopefully illustrate why it is you get these amines when you reduce amides. Okay, and again, we talked about this before, and the difference with some of these LAH mechanisms is the fact that we oftentimes make this assumption that LAH is simply H minus, and it's not. That aluminum, or group 3 metal, more generally, plays a role in these reactions, right? The aluminum, or the boron, is a Lewis acid, and it functions that way in these mechanisms. So perhaps a better way of thinking about this would be, as the hydride adds in, and you make that O minus species, the O minus is a strong Lewis base, and it will end up kind of coordinating with the Lewis acid in something like this. So you make this kind of aluminum complex. And then in a simultaneous step, you can kind of imagine the nitrogen kicking in and helping to push the oxygen and aluminum out. So basically, this aluminum complexation is making that oxygen into a better leaving group as it leaves as an organometallic complex. If you kind of follow those arrows through, what you end up making then is something like this, to which another hydride, so this kind of iminium type species, and hydride can then add again, giving you the amine. Okay. So again, you don't necessarily need to know this mechanism. I just wanted to show it to you to illustrate a point as to why is it that these amides behave so differently in reduction towards all of the other derivatives that we see. Okay? The important thing that you need to know is that when you reduce amides, you end up making amines, not primary alcohols like we've seen for all of the other derivatives. All right? Any questions on this? Okay, then we'll move on to the next one, and this is going to be hydrolysis. So you should, even without knowing the mechanism, be able to predict what the product should be from hydrolysis. Right? Because think of the definition of carboxylic acid derivatives. The definition being they give carboxylic acids upon hydrolysis. So we've got to make some sort of we've got to make a carboxylic acid here somehow, right? So in hydrolysis of amides, you can do this under 2 conditions. We can do it under acidic or basic. So let's go ahead and do acidic first. Now again, neither of these is going to be easy to accomplish. And so if you want to hydrolyze an amide, you're going to need at least 6 molar HCl, boiling, long reaction time. Okay, it takes a lot of work. But when you do that, the first step, as with all of these, is you're going to go and protonate the carbonyl. And as with all of these, that serves the same function, making a stronger electrophile. And at that point, the water can come in to attack the carbonyl. And I'm just going to do a minus H plus step to get everything back to neutral. All right, at this point, we know we've got to get to a carboxylic acid. We know that the NH2 can't really just leave as NH2 minus. So what do? Yeah, protonate the NH2. And that makes sense. We have a ton of protons around because we're under very strongly acidic conditions. So we can just protonate that guy. That will convert it into a good leaving group. And then we reform the carbonyl and make it leave. And in the final step, just lose an H+, and that will give you the carboxylic acid, which is required because it is a carboxylic acid derivative, and then the amine as your final product.
So Professor, we have to do a deprotonation before doing the protonation for the amine?
Yeah, you've got to protonate this guy because otherwise it's a terrible leaving group.
No, I mean the step above it.
Oh,
Do we
right.
need to deprotonate that?
Yeah, that's what, so you're doing a minus H+ step right here to get rid of the proton on the OH.
Does that have to be before the protonation of amine? Or
Yeah, because otherwise you're going to get a double positive species, which
okay.
you don't typically see. And again, you can show this is catalytic. We use a proton there, we got back a proton there, we use a proton there, and we get back a proton there. All right. Okay, then let's go on to how this proceeds in base. So doing this in base is even harder. You need about 40% sodium hydroxide, boiling conditions. This is quite difficult to do for a reason I think you'll see become clear in just a minute. So if we're trying to do the same hydrolysis in base, the hydroxide will attack straight away. And so we end up here after the first step. Now what we did, so we're kind of in the same place here that we were in here under the acidic conditions. So the nucleophile has added, we've made a tetrahedral intermediate. Now, based on the nucleophilic substitution mechanism, we need to reform the carbonyl and kick out the leaving group. So that was easy enough to do under acidic conditions because all we had to do was protonate the NH2 to turn it into a good leaving group. Can we protonate the NH2 and turn it into a good leaving group here? Not in 40% hydroxide. There's not a proton to be had. So we're going to do a little trick that we did back when we did basic ester hydrolysis, and for the same reason. So this step is not a favorable equilibrium, obviously, because we're kicking out an NH2 minus, and I just told you that you really can't do that. But imagine what happens if that can occur even to a minuscule extent. Look at what you get. You get an exceptionally strong base in the presence of a pretty darn strong acid. These two will not coexist, because as soon as just a couple of them form, there is a massive one direction arrow as the strong base deprotonates the strong acid. So this is really just a Le Chatelier thing. You have a really terrible equilibrium step here on account of kicking out an NH2 minus leaving group, but as soon as you do, even if you form just a couple molecules, these two immediately react. So we are continually removing the product of a bad equilibrium. And Le Chatelier would predict if you're continually removing the products, the equilibrium will shift to make more of them. Okay. All that said, this is very hard to do. You really have to push on it. All right? So if you're ever trying to do amide hydrolysis, you're not probably going to try to do it under basic conditions. I guess the bottom line to that story is, if you ever got to get rid of a body, you want to do it in acid, not in base. Right. Bodies being mostly protein, proteins being amide bonds. So, anyway, any questions on the hydrolysis reactions? Okay, the next few you already know. So just to kind of put everything in one place. Something else that we can do with the amides is the Hoffman rearrangement. So we won't go through the mechanism of this because we already did that back when we studied amines, but you know that you can take amides, and by the way, the caveat here is it must be primary amides. We can treat that with a molecular halogen, strong base, water and heat, and again, all that does is it takes that carbonyl and it cuts it out, it loses it as carbon dioxide. And it just stitches the remaining two pieces together. Okay. And if you're unsure of the mechanism of this or want to revisit it, just go back to the amines chapter. We went through it there. Okay. And then the final one, I think I mentioned this the last time to you, and this is sometimes a useful synthetic step. And primary amides can be dehydrated. This is also only available for primary amides. So if you think about something like that, if we're going to dehydrate, obviously that means a loss of water. So if one of our products is water, H2O, there's only a couple places that can come from with primary amides. Notably, the oxygen's got to be that one, and the hydrogens are probably going to be from there. So if you think about redrawing the primary amide without that H2O, what you get is something that looks like this. Obviously, that is not a viable structure in that form. To ensure that everything has its octet, we will make a triple bond. So this is a really nice way of making nitriles. The reagent that you typically see for this is either phosphorus oxychloride, POCl3, or you can even do it with thionyl chloride. All right. Any questions on this? Okay, that's the end of amides. Oh, notice what we didn't do. There was a reaction that we have done for all of the derivatives up to now.
Grignard.
Yeah, the Grignard. Why are we not doing Grignards with amides?
Cause the NH2 is a protic.
Yep, exactly. Because remember, that is one of probably the most significant limitation to using Grignard reactions, is you cannot do them with any kind of functional group that's remotely acidic. Basically what that means for you is anytime you have heteroatom H, right, alcohols, carboxylic acids, thiols, amines, amides, any functional group that has heteroatom H, you cannot do a Grignard because the Grignard will deprotonate them. So no Grignard reaction here. All right. Okay, so then let's go on to the last of these derivatives, which are the nitriles. So like before, we'll go through the synthesis first and then we'll look at reactions. So I think you know all the ways of synthesizing these already, but just to kind of put them all in one place, we can do SN2 chemistry with cyanide ion. We've seen this before, where the cyanide ion, being a good nucleophile, can just come in and directly substitute the halide, SN2. So that's an easy way of making these nitriles. Second way is dehydration of a primary amide. We just talked about that 3 minutes ago. So I'm just gonna write C above. Third way that we've talked about that you already know is through cyanohydrin. So this goes back to aldehyde ketone chemistry. The most common way this is done anymore is taking a aldehyde or a ketone, reacting it with a cyanide salt and a protic solvent. So the cyanide will attack straight away. And then you end up protonating the alkoxide from the protic solvent. And then finally, this one is a little bit limited, but we can make aromatic nitriles through diazonium chemistry. So starting with some sort of a aniline type compound, we first make the diazonium with acidic nitrite. And then using one of those Sandmeyer reactions, the copper-based reactions, we'll use something like that. And that makes the aromatic nitrile. All right.
Professor,
Mhm.
can you use HCN?
Yeah, you can use HCN as well. It's just kind of like with the cyanohydrin reactions, people don't like using HCN very much these days because it's very, very hazardous. It's very volatile, and if you breathe any of it at all, it's probably going to kill you. So people tend to not use it very much. Okay. Any questions on the synthesis here? So like I said, I think we've talked about all of these before. Okay, then let's move into the reactions. Let's start with hydrolysis. So we'll look under acidic and basic conditions. Now, again, we know what we have to get to from the hydrolysis of these, because by definition, because they are acid derivatives, that means when you hydrolyze them, we must get to ultimately a carboxylic acid. So let's see how that's going to happen here. So the CN triple bond is very similar to a CO double bond. It's just a highly polarized carbon heteroatom multiple bond. And as a result, it's going to behave much like a carbonyl does. Right? So if you put it in strong acid, the first thing it's going to do is the nitrogen with its lone pair is going to go grab a proton. That makes the carbon much more electrophilic, and water can attack. So we get something like that, and we will do a minus H plus step to get things back to neutral. And then what we're going to do is, again, if we're trying to make a carboxylic acid, we've got to lose that nitrogen species, right? The nitrogen part of this guy. And so probably makes most sense to think about trying to get it protonated so it can leave. And again, that makes sense because we are under strongly acidic conditions. So I'm going to bring the electrons down. And if we now remove the proton, just do a minus H plus step, look where we end up. We end up with a amide. And so then this continues. We just looked at the mechanism of this. So in the end, so you can just kind of review those steps, the amide hydrolysis that we talked about earlier, but in the end, the product that you're going to make is that. We can do this in base as well. Hydroxide will go in and attack straight away. Oops, that's not how to do that. There we go. the nitrogen will end up protonating from water. Then, let's see. What I'm gonna do here, we still have strong base. So in kind of a simultaneous step, the hydroxide can deprotonate there. Shift electrons this way. And then that protonates from water again. And like in the previous example, you're left with that intermediate amide, which through the mechanism we saw several minutes ago is just going to do amide hydrolysis. So in the end, what you would make is the carboxylate.
What do the 3 arrows mean?
Sorry?
What do the 3 arrows mean?
Oh, it's just a bunch of mechanistic steps, right? All of those steps that we did in the previous chapter where we looked at the hydrolysis of amides, that's all that's going on here.
So it's kind of like et cetera.
Yeah, yeah.
Okay.
I just didn't want to go through all of those amide hydrolysis steps again because that would be very tedious and time consuming, and we already looked at it
Okay.
during this lecture. So yeah, I just kind of abbreviated some steps there. All right. So as we can see, as we defined the carboxylic acid derivatives at the very beginning of this chapter, being functional groups that hydrolyze to give carboxylic acids, all 5 of these have proven to do that. All right. Yeah.
When you form the carboxylate ion,
Mhm.
could you add like a primary alkyl halide and do an SN2, or is that not typically how it's
You
done?
could, you probably wouldn't just throw it in at the end because that would get really messy. Because I mean, you got to think about it, you got a whole bunch of base in here, right?
Mhm.
And if you just threw in alkyl halide in the end, the hydroxide is more than likely going to go in and attack that alkyl halide before the carboxylate would. It would just be messy chemistry. But you could isolate the carboxylate. You probably need to protonate it and make it a neutral carboxylic acid, and then take that on and do chemistry with it. But yeah, you wouldn't typically just throw in some alkyl halide at the end of the process without purifying first. Okay, let's look at reduction. So we can do reduction of nitriles as well. And just as before, the reducing agent of choice is going to be LAH. So again, we can think of LAH as an H- species, and that's going to attack the carbon. And that's going to happen one more time. And if you do the mechanism in this simplified way, you get kind of an odd result. Because it gives you a double negative, which upon acidic workup you end up making the primary amine. Now, again, you can see the complication that we sometimes will run into using this oversimplification. You know, the oversimplification here that we're making is that LAH is simply H minus. And that's what is leading to this kind of bizarre double negative intermediate. Now, that's really not what's happening, like we've talked about on a number of occasions, that aluminum plays a role here. And probably a better way of thinking about this is that at this stage, you don't have just an N minus. N minus would be a strong Lewis base. The aluminum is a strong Lewis acid. So at this point, what is probably more realistic is instead of doing this kind of simplified intermediate, you probably have aluminum complexing. Something like that, which then another hydride from the aluminum can add in, giving you kind of more reasonable intermediates. Okay, you don't have to worry about this. Again, I'm just showing it to you to kind of help explain why we see this weird intermediate. The weird intermediate probably doesn't really exist, but it's helpful for simplifying our mechanism. It allows us to avoid organometallics in our mechanisms. Okay. Okay, the last one of the chapter. By the way, should we be able to do a Grignard reaction with the nitriles? Anybody see a problem with that, or are we good to go with that?
I think we're good to go. There's no
Yeah,
reason.
exactly. I think we're good to go because the difficulty, the problem, is whenever you have a heteroatom H. We don't have that in the nitrile, so we should be able to do a Grignard without a problem. So let's go ahead and see what that's going to look like. This one is interesting because it gives you something that you're probably not expecting. So we'll just do the methyl Grignard. So again, oftentimes with these reactions of nitriles, you can think of the CN triple bond very analogous as a carbonyl. So in the same way that if you take a carbonyl and treat it with a Grignard, the Grignard reagent attacks the carbonyl carbon. Same thing's going to happen here. The carbanion nucleophile of the Grignard is going to go in and attack that carbon. Now, it might be tempting to think that at this point, look at the previous mechanism. You know, in the previous mechanism, you had kind of the addition of the nucleophile, and we got here. That's pretty much where we are at this stage, right? One equivalent of the nucleophile added in. If you think about the reduction, what did we do? Well, we had a second equivalent of the nucleophile add in. That is not what we are going to do here. And again, this goes back to the metal. There's a big difference between aluminum and magnesium. Aluminum is a strong Lewis acid, magnesium is not. So the magnesium cannot, again, this goes back to that kind of simplification that we've been making, and sometimes it works well for us and sometimes it not so well. That simplification ignores the metal. and it really plays an important role sometimes. You cannot complex this nitrogen with magnesium. It is not a Lewis acid. And so what that means for us in a practical sense is you cannot have a second equivalent of the nucleophile add in at this point. So what happens? Well, pretty much nothing. Until you work it up under acidic conditions. Every Grignard we do, we always have a acidic workup step. And that will end up protonating the nitrogen. Skip down here. Well, you think about this. During the acidic workup step, we have dilute acid. What is this functional group we've made right here by protonating the N-? It's an imine. It's going to test your memory here, back from Unit 2. When we have imines, normally we make them by taking an aldehyde and treating with a primary amine under acidic conditions. If you recall, all of those steps were completely reversible. So you can make an imine under acidic conditions, but you can also hydrolyze an imine under dilute acidic conditions. Well, we just happen to have dilute acidic conditions here and an imine. And so this is not going to be stable under those conditions. Instead, it is going to, under these conditions, it's going to hydrolyze. And when you hydrolyze an imine, what you end up making is the ketone. So an interesting little twist in the mechanism.
Just a question, with the Grignard and reactive ketone?
That is a really good question, and that's what I was going to bring up next. So, up to this point, go back to the different derivatives that we've seen that do Grignard reactions. The acid halides, the anhydrides, the esters. In all of those, you end up with an intermediate ketone, and then the Grignard attacks a second time, and you get a tertiary alcohol. What's the difference here? Why am I not continuing on to have the Grignard attack this ketone? Well, it doesn't really need a leaving group when those Grignards were attacking, because the Grignard would just come in and attack, you'd make an O-, and then that would just hang out until you protonate it.
Isn't it a completely second step, like separate from the Grignard?
Yeah,
See, the
exactly.
Grignard's not there anymore.
That's the point. We've already killed off all the Grignard, right? Because all of this process of hydrolyzing the imine happened because you already added the acid. At the point you add acid here, there's no more Grignard around. It's all done. So at this point where you've made the ketone here, you've long since killed all of the remaining Grignard.
So the acid's reacting with the Grignard? Is that, okay.
Yep. Yeah, so even if you had an excess of Grignard, which you probably wouldn't because it would be pointless, but even if you did have excess Grignard, at the point where you started to work up the reaction here, any excess that were around would have been quenched. Okay. But that's a really good question. Why it seems very counterintuitive that we're doing a Grignard reaction and isolating a ketone. But it has to do with order of addition. Any questions there? So this would be the end of the unit 3 material. Any questions on any of the material from today or any of the previous Unit 3 material that you would like to discuss?
I just have a question about the tests. On one of the practice tests that we worked on, it had a lot of math spec questions.
Oh,
Should we
no.
work on
Don't worry about it. You're not gonna have any mass spec on this exam. The reason why it was, I revamped the unit structure for this class a little bit ago. And so any of those exams that had mass spec came from before I revamped the unit structure.
that?
So no, you will not have any mass spec on this exam. Okay, then what I thought we would do, we'll probably just spend the rest of today looking at it, because that'll give us maybe 10 minutes, 10-15 minutes for you to look at it, and then a few minutes to go over it together. But I thought I would go ahead and just give you a mechanism problem to practice with. I'm gonna actually stop recording here. Sorry, I gotta erase the answer before I show it on the screen. Okay. Forgot to erase those arrows, but anyway, there's a good first step for you. So what you're gonna do here is you've got these two things that are reacting with one another. You're gonna form an intermediate, and then that intermediate is going to react with acetyl chloride to get to this. So why don't you, and again, y'all can work by yourselves or with others if you like, but take, I don't know, 10 minutes or so and see what you can do with this mechanism. And then we'll